No i problem. Dobra, widzę, że ładuje się. No więc musiałem sobie użyć drugiego komputera, chociaż podejrzewam, że wejście też z telefonu by spokojnie dało radę. Jeżeli
Ale z
chodzi
telefonu
o...
nie masz takiej obsługi,
O,
jak
dobra. To...
przynajmniej ja nie umiem tego tak
Tak.
tak fajnie jak
Jakby co,
umiesz.
jesteśmy już live na YouTubie. Czekaj.
So from now in English.
Okej.
Good afternoon.
Good afternoon.
Hello,
Mariusz, hi.
Good afternoon.
Good to see you.
Yes.
Sure. Unfortunately, not in person, only on the screen.
We all miss to the personal meetings. There is no doubt.
What a pity. Hopefully next year will be better.
Yeah, we hope. Due to vaccination, we hope that the situation will be much better and finally we can meet during the conferences. It's really a pity because almost last year and this year will be no IEEE conferences. So it's like almost 2 years without the conferences.
You mean at all? Even remote?
No. I think that the in-person conferences,
Yes,
of course, helpfully that we have such tools like Zoom and other tools which help us to organize the conference, but it's still not the same. For us, it's fine because we have the chance to meet each other. But for the young researchers, to build the sub of collaboration, the links, I think it's terrible.
Yeah.
May I try to share my screen to check that?
Yes, you've become a co-host, so you can share the screen without any problems.
Okay. Okay, just. So do you see my
Not
slide?
yet.
Not yet?
Not yet.
Okay, maybe now.
Yeah.
It's loading.
Yeah.
We can see it.
Works fine.
Okay, so I will stop share my screen. Am I ready?
We have to wait for audience a little bit. We have 7 minutes according to the schedule. It's quite nice.
I think we were lucky with PEMT according to the number of papers, because the shift of 1 year was finally a good decision, I think. Because starting a new conference, what I have heard from other conferences, that the 21 editions from the other conferences all have very few contributions.
Yeah, in the beginning, the loss was, when I look in IEEE, the loss was not so big because it was lost like a 30%, 20-30% less of papers in comparison to the previous years when it was in-person conference meetings. So in the beginning it was not bad, but if the situation is continuing in the same direction, that it's only virtual online meeting, it's less and less participants.
Yeah.
So I think that the results of PEMC is really good. It's really good.
Mm-hmm. And taking into account that in September it was around 50 papers because many people resign.
Mm-hmm.
So now it is good achievement, I think.
But this year, I guess there will be no in-person meeting. As far as I've heard, there is no chance. No country is risking.
Mm-hmm.
Yeah, the countries are waiting what happens in the second part of the year. Of course, they waiting how the vaccination be also resistant for the different version of the virus, which we are sure that happens in the future.
And the worst scenario, the medicals people are aware of, is a conference where people from all over the world meet within a few days, exchange all mutations and viruses, and then go back to their home countries.
Yeah.
They are not very. They don't like the ideas of conferences at the moment.
But they are also good point of pandemic because, for example, in my university, plenty of people get to know how to use the modern tools to teach.
Yeah.
And I think that in the future, we will use those tools more frequently. For sure, if we have a labs, we cannot replace the labs by Teams, by Zoom, but from time to time, the lectures can be organized this way.
Yeah.
I had all the time the problem traveling all over the world that I have to move my lectures, to reorganize everything, to make a new schedules with students. But now I just switch on my computer, continue my lecture exactly as is in the schedule, and I think that it's helped me in this situation. However, the labs,
It's
we have to come back.
But anyway, we switched to remote education. Distance learning.
But it also shows that I don't know how in your universities, but we have some of the computer labs when the students just in the front of the computer did some of the simulations and so on. But I think it can be replaced by online, by virtual with students. But only what cannot be replaced is a project and consultations and real hardware lab, which is never be replaced.
Hardware experiments.
Yeah.
Even some remote experiments, but they are single in the whole curricula, so it is impossible to cancel real laboratory exercises in the real.
Yeah.
Yeah, so we have 3 minutes. How many participants? 6 still. Wow.
We're keeping everyone in the waiting room until the almost exact hour, so that we have quite a bit quiet over here. I have a question to chairs. Will you be presenting something about the Professor Malinowski or not?
Yes, I think so.
I mean, like in the form of presentation or something like this, like a slides, whatever.
I am not prepared.
Okay.
So I guess that probably because I am from Poland also, like Mariusz, so the better solution would be if you, Thomas,
sure.
as we discussed by emails. Okay?
Yeah.
So I will say hello to everyone and then switch to you, okay?
Yeah, sure.
Yeah, fine.
Sounds good.
Okay. Thank you.
So maybe we'll start bringing up the people. We have currently 15 in the waiting room. So if we have everything ready, I guess we can start bringing up the people.
Yeah, okay.
I'm ready. I don't know how the chairs, but
Me too.
You're prepared. One minute left.
Hello. Hello, who are you? I think we have not too much participants as I can see here.
we have 23 totally.
Yeah, but we need more.
Shall we wait a few minutes more?
Yeah.
Mariusz, what do you think?
Depends on our presenter.
So what about the video? It will be available for all participants later?
From this keynote?
Yeah.
Yes.
Okay.
At the YouTube channel will be possible to see again.
Yeah, because
I see that more participant is connecting, so maybe 1 minute or two.
Yeah,
we have.
So we shall wait.
Yes. So
at least
my suggestion is to wait 2 minutes.
Yeah. Okay.
Schedule time.
Okay. Thank you. So I think that we should start. Okay.
Yeah, sure.
Okay, so good afternoon, ladies and gentlemen, dear participants of PEMC conference. My name is Teresa Orlowska-Kowalska. I would like to welcome everyone present at the second keynote session of our PEMC conference. I am from Wrocław, University of Technology, from the Department of Electrical Machines, Drives and Measurement. I have pleasure to co-chair this session with Professor Thomas Wolbank from Vienna University of Technology, from the Department of Energy Systems and Electrical Drives. I would like to ask Professor Wolbank to presenting our keynote speaker, Professor Mariusz Malinowski from Poland. So Thomas, please introduce Mariusz for our audience. Thank you.
Thank you, Teresa. Welcome, everybody. Good afternoon, good morning, good night, wherever you may be at the moment. It is a pleasure and an honor for me to introduce our keynote speaker, Mariusz Malinowski. Actually, it's not necessary to introduce him because everybody of you already know him very well. Mariusz received his PhD and DC degrees in electrical engineering from Warsaw University of Technology in 2001 and 2012, respectively. He was a visiting scholar at Aalborg University in Denmark, at the University of Nevada, Reno in US, the Technical University of Berlin in Germany, and finally at the ETH in Zurich in Switzerland. He's currently with the Institute of Control and Industrial Electronics at WUT. And his research interests includes control and modulation of grid-side converters, multi-level converters, smart grids, and power generation systems based on renewable energies. He has co-authored more than 130 papers and 6 books, holds several patents, and he received numerous awards. Counting them is nearly impossible. Besides his scientific merits, he also very active or puts a lot of effort in our scientific community, and he's president-elect of the Industrial Electronics Society. So Mariusz, very glad to welcome you here, and the floor is yours.
Thank you very much for this kind introduction. Thank you very much for the opportunity to present some of my thoughts about the smart transformer. Let me to share my screen. Just only please confirm that screen it's visible.
Yeah.
Okay.
Okay. So thank you very much. Just only the. Okay, now I can start. So preparing for this lecture, this is what I did. I first check, is the power electronic transformer solid state transformer or smart transformer? It's a hot topic for power electronics researchers. Of course, we can find this terminology as a keywords in the many of papers. And to answer for this question, I found that only during the last 10 years we can find over 400 journal and magazine papers related to those solid state transformer, smart transformer, as I told, if we include the special functionality, and even over 1,000 conference papers. So this is just a proof that the topic of the smart transformer, it's very popular now. And the question is, what's the motivation for the researchers? So when we move to the motivations, we can find that first of motivation is the increased consumption of the energy around 2% per year. The second, the increased market share of renewables. What we can see that in 2014, for example, the steel coal, it's a dominant in the energy mix, but some of the forecasts for 2040 is that the portion of the renewables will grow up. And I think that this is also one of the motivation when we are looking for modern solutions, power electronics solutions. If we look more deeply for this motivation, I think the good example is a PV. This slide showing how the PV, how the cumulative power growing up in case of the PV, and at the same time how the price of PV powers dollars per watt is going down. So we can see that now currently it's really below 50 cents per watt. Even more wider time window can show that how drastically this price of the PV panels drop down. But this is only motivation which bring us to the biggest installation of PV. We can see that the PV plants currently it's normal that they are even over 1 gigawatt. And we can find plenty of the installation all over the world. The another motivation is increased market share of the energy storages, especially those energy storages due to the drastic drop down of the price of the batteries. We have an example of lithium-ion batteries, which was dropped down last 10 years 7 times. Therefore, the attractive solution now is to install them in the PV systems. And we can see such installation, which help the PV operator in the power factor or VAR support, voltage flickers, spinning reserve, frequency control, and what is also important, supply security. If we even forecast for the future, we can see that even predicted it's more drastically drop down the price of the lithium-ion batteries, which will be prediction for 2025. It's $94 per kilowatt, and in 2030 it's $62 per kilowatt. What brings us to many of the installations for power system, we can find that those installations with the energy storages, big energy storages are bigger and bigger. We can find easily even the 300 megawatt hours energy storage, but such installations are growing in each country because the power system operators, they see some of the chance to install more and more energy storage subsystems. But if we go more deeply, what else? Then we can find also the fast development of distribution generation or even the smart grids. We see plenty of the modern elements in the power system, including the power electronics converters, which of course helps to solve many of the problems, like provide the reduction of environmental pollution and global warming. The generally system is modular and redundant. Also, we have they are installed close to the load, what can reduce some of the losses in the system. And of course, the operation of easy standalone is possible. Moreover, if we are thinking about the transaction energy concept, then we need additionally some of the hub. But currently, the classical transformer, they have some of the drawbacks. In the point of the smart grid, it should not operate with heavy distorted and unbalanced voltage. It cannot compensate higher harmonic and control power flow. Therefore, the new system, they demand some of the new hub, and this new hub should aggregate smart sources like renewable energy sources, electrical vehicles. There are more and more electrical vehicles, smart homes. Also can minimize the power flow and grid distortion, allows easy connection of the energy storages, as well as should be able to exchange information about the price market of the electricity. What I told, it brings to the idea of the transactive energy, and such a hub can be realized by the smart transformer. This is we can find similar solutions with the terminology of the power electronics transformer, solid state transformer, but the smart transformer, this new terminology appears because it's not only the power electronic, it's also plenty of the new functionalities which is surrounding the converter. One of the most important advantage of such smart transformer is that we have in the same system DC and AC grid. What make a possibility to build such a hybrid system if we are thinking in the future that our system will be DC, what some of the visionaries they tell that future system will be the DC system, then smart transformer help us for this transition, because at the same time we have available AC and DC grid. It help us, for example, to connect directly charging stations on the low voltage side, on the medium voltage side. We can connect directly the PV panels without additional energy conversion stages. We can integrate easily energy storages, what absolutely improve the efficiency, total efficiency of the whole system. Of course, there are plenty of the advantages. There are proper operation after failure of the grid. We can implement the post-fault operation idea, proper operation under the voltage unbalance. We can increase the efficiency because we can dynamically control the power distribution or power flow between the medium voltage side and low voltage side. As I list the more and more advantages, then we have to list also the reactive power and higher harmonic compensation, which can be independently done for the both sides of the transformer. We have dynamic voltage control, and also we have provided the communication with the other elements of the transformer. As well as we can also provide, which I show you later, that we can provide the full control of each individual phase and simple aligning mode of operation. The idea is not new, and the topic is not new. We can find it in the paper of the Professor Kolar, which shows the patents of the McMurray. So we can see that in those patents, the cascade connected converters, which are used in this AC-DC conversion stage, was patented in 1969. So we see that the patent is even older than PMC. Also, the dual active bridge, which is one of the key point topologies for the smart transformer, it also was patented in 1970. So it's a 51 years old patent. However, recent technology development, like high-frequency transistors, high-frequency transformers, and solid-state transformers, make this industrial application more visible. When we look for general, many of the papers, when we track many of the papers, so the idea of the capacity of the solid state transformer is very wide, including many variants of the conversion stages. One of the variants, it's what we group, it's a single, because the one single phase high frequency transformer is used for each of the proposed conversion stage. We have no time to present inside the available topologies or presented published topologies, but you can find detailed topologies in this Industrial Electronics magazine paper, which was published in 2000. If we go to another group of the topologies, we can distinguish also the multi-port, which is showing that they are some of the multi-winding high-frequency transformer-based topologies. And also we can find a group of the papers based mainly on such kind of the transformers. And the last group of the solid-state transformers, they are called modular because they present the modular architecture. We have a multiple DC-DC converter with single phase transformer, which then it's used for the future composition of the solid state transformer built from the models. However, the most popular are two topologies, which is called modular multi-level converter. So solid state transformer is built on the modular multi-level converter, or this one when we have cascaded connected converters on the medium voltage side and parallel connected converters on the low voltage side. And in the rest part of this presentation, I will focus mainly, and I will show the examples of this topology. So if we look generally, the topology of the smart transformer, it's divided for three parts: AC-DC conversion, DC-DC, and AC-DC conversion. This part is based on the cascaded connection of the modules, which make a possible operation on the medium voltage side. Then we have the DC-DC conversion, which transform the voltage from medium voltage to low voltage, and it's based on the input series output parallel configuration, including the high frequency transformer. And we have DC, AC, low voltage conversion, where the converters are parallel connected, and it's demand high current because it's demand high current on the low voltage side. As I told, because we have such configuration, then it's natural that it's a modular system, and modular system help us, and generally this that we have a multi-stage system. It helps us that we have the more terminals, which I show in the previous slides, give an opportunity to connect to the medium voltage AC grid, to medium voltage DC grid, to low voltage DC grid, and to low voltage AC grid. But the modular system, which is generally brings a lot of advantages, and those advantages are listed here, which is like unified building blocks. They give opportunity for scalability, efficiency management, and other more advantages. Also, it's good for reliability point of view, because we have a multi conversion channels. We have the service we can do service during the operation, or the last publication showing also the power routing, which also help to provide longer operation of the system. But still, there are a lot of demands, a lot of challenges, especially in the distribution control, because there is a lot of effort to provide the good communication, synchronization, real-time, process data. There is a complex from communication point of view system, and many other difficulties. And the big challenge which have to be done, it's how to prove, how to convince the colleagues from power system operators that the solid state transformer it's a chance, it's an opportunity. How to prove, taking account that when we see that the lifetime operation time of many of the devices, it's real long. So in case of the transformer, which is a lifetime, it's predicted for 40 to 60 years, where the transformer is working 24 hours a day. And how to provide and to convince that the power electronics transformer, including the thousands of the components, which can provide to the fault, which is also shown here, and the many factors like semiconductors, capacitors, PSB can bring the fault. It's a power electronics transformer. It's an attractive solution. Moreover, that it's environmentally many factors also including those risk of the fault. So, summarizing the challenges which have to be solved before the real application of the smart transformer in the power system. It's the codes and standards of the before the integration of the solid state transformer into electrical system. The another is cost, and also we have to tell about the reliability. And we have to also take into account short circuit capability and communication. So I think that those lists shows that it's a lot of challenges to do before commercial commercial launch of the solid state transformer in the system. So let's look first to the how to maybe skip or to find some of the solutions for the first conversion stages from AC/DC and DC/DC, because they are somehow a little bit coupled and it's difficult to analyze them separately. First, some of the topologies in case of the reliability or post-fault operation, let's say. How to provide the post-fault operation. And in the papers, we can find the different solutions. We can find on the switch level redundancy, where series of parallel transistors are added to each module, but it's difficult from design point of view, especially for high frequency converters, because if we currently considering the such solid state transformer, we are thinking especially on the transformer based on the silicon carbide components. And due to the stray inductances and capacitances, it's difficult to do. The another option, which is shown here, it's a leg level redundancy, where the extra transistor legs is added to each module in order to possible reconfiguration. I think that this possibility is quite easy to be realized. We have the module level redundancy when extra modules are demanded, but it's costly. I think that this solution is more expensive. And we have the absolutely most expensive solution, which is a system level redundancy, but analyzing everything, variable reliability versus cost, or the post-fault operation ability versus cost, this one, it seems to be more attractive because provide increased reliability. It's support overloaded branches and increase fast short circuit power. And how it can be done. This is just only the case showing that some of the extra leg can be implemented. On the this side, on the low voltage side, it can be done by some of the extra standalone branch. If we have some of the failure in one of the in the leg, then the switch which bypass this faulty leg, making operation this extra leg. To reduce the number of the transistors, the same leg can be used for the both converters, so for the cascade connected converters or on the dual active bridge converter, which minimize the number of the transistors. However, it make also possibility to replace the faulty leg. But this is what the previous slide shows. A very easy, very simple possibility. However, the more complex be the how to make a configuration for the whole system. So if this converter connect in this way to the solid state transformer, when there is a one leg, then it's easily, of course, to operate when we lost, for example, this module, because it can be bypassed. But the problem, it appears when we lost the module on the low voltage side, because in this situation, we lost the full phase, which is indicated here, and we have some of the unbalance of the grid. Therefore, the proposed also solution is it's not like vertical, but rather horizontal configuration of those previously presented converters, because even if we lost full, one layer of the converters, we assume that we have more than 3 layers. We have plenty of such converters. There is not significant loss of the power, and moreover, we have all the time symmetrical loaded the phases. There's some of the just only example that such model was built in our team. You can see also that is a quite pretty design, including also the high frequency transformer. The power of the module is 3.5 kilowatts, and especially like a heart of the system, it's if the high frequency transformer, and this high frequency transformer in this situation was built based on the PCB. So this is easy solution, fully recommended, because it's give a good performance. But if we compare to the commercial transformer available, for example, we can compare to the Python transformer, then we reduce the price over 10 times. But the another performance, the parameters are almost the same. Even we reduce also the size of the transformer. So this is just only solution how to simply solve the problem of the high frequency transformer for such application. But let's analyze some of the functionalities, because as I told you that the power electronics transformer it's like a topology with simple control. But if we are thinking about the smart transformer, we should consider the another functionality which are available for the system. For this additional functionality, we can distinguish the full active and reactive power control. We have a bidirectional energy flow, of course, the post-fault operation, higher harmonic compensation. We should provide the sinusoidal grid current, and we can provide the grid support in case of the fault. We also can use different control methods to make a symmetrization of the power. As I told you previously that it's important to convince the colleagues from power system operators. Therefore, we did some of the study how this solid state transformer and classical transformer will operate in the subsystem, which is shown here. This is the IEEE model analyzing the medium voltage subsystem. We can distinguish here, you can see this transformer, which is shown here, and we distinguish two nodes. Node 650, which is the nodes connecting with another medium voltage subsystem, and node 633, which is just in the front of the primary side of the transformer. And what we analyze, we analyze how looks the current in node 650 and in node 633 when we have the classical transformer, when we have a lot of nonlinear loads, and when we have the smart transformer. So you can see that smart transformer significantly improve the operation and performance of the system, because the current is fully sinusoidal. If you need more details about this, just I recommend to look this paper which we published in 2000 in Transaction of Power Delivery, when we did this deep analysis of the operation of the smart transformer in the power medium voltage subsystem. In smart transformer, it's so complicated from power electronics point of view that we have a lot of variables to control. So we can see here plenty of the variables on the medium voltage side, medium voltage AC to DC, many variables for DC-DC, and also DC-AC on the low voltage side. And also we can use some of the feed-forward signal. We can help us to provide better operation of the system, better operation from the power system point of view, because this is our client. We have to convince the colleagues from power system that our solutions is attractive, and we show that using this feed forward, it's able to provide for power system operation different operation modes. For example, constant power, symmetrical grid current, or even the grid support for phase, which is have to be unloading. For example, if there is some of the short circuit and the voltage drop in this phase, we can also provide the lower current for the grid operator. So I think it's a big advantage because it depends what the grid operator needs, then we can provide such operation function. And we go now to this AC-DC conversion stage on the low voltage side, which have to be composed from parallel connected converters. Of course, there's some of the demands for this configuration. We have to have multiple 4-leg modules because we are working on the low voltage side, and we should have a reconfigurable legs, which is also a challenge. And the another challenge is it's to provide the control synchronization, reconfiguration scenario. We have to have a distributed control and real-time communication. So first of all, we consider which kind of the converters. The easy answer was that it should be three level converter, because we know that 3-level converter provide some of the passive components reduction, at least a 30% reduction of the passive components. But the question was how these 3 different topologies, including the NPC, flying cap, and T-type, how resistant for the faults which can happen. And therefore we analyze first the open switch fault, and then analyzing these different topologies, we prove that the T-type converter is the best option, because even if there are some of the faults in the transistors, we can still somehow provide the operation. And another option that the open with the closed switch. And with the closed switch, also we analyze the different scenarios, and in this case, the NPC and T-type was equal. But finally, using both scenarios, the T-type was the winner, and therefore we decided to use the T-type in final configuration, which is shown here, showing that we have some of the flexibility to connect so many, for example, legs to the one phase, which helps in case of when the one phase is overload. And when it's overload, we can connect more phases to this phase to help. Therefore, you can find also that some of the prototype of the modules was built based on silicon carbide components to check this functionality. And another functionality which have to be provided, besides of the basic, like a bidirectional energy processing, or providing the high quality of AC voltage, or the stable operation and fault-tolerant capability, we have to also discuss some ancillary services like microgrid management, reactive power compensation, load identification, and impedance identification, which is also attractive solution. And to provide the very high quality voltage in the output, should be considered some of very simple block, which is shown here, which provide the harmonic compensation. Because if we are using the rather small capacitor in the DC-link, and we have strongly nonlinear loads, those can influence the quality of the voltage. But if we use a very simple block of harmonic compensation, which is measure the voltage on the capacitor, and we are using the high pass filter just to compensate those distortions, then we can provide sinusoidal current easily, even if we have different distortion. And what was also demanded, as I told, that each leg it's of the such 4-leg converter, each leg is treated as a single phase converter. Therefore, there's not control in DQ. There is rather control is stationary rotating system based on the PR controllers, because in this situation give us some of the freedom connect any phases as possible to any legs as possible to as needed to the phases. And some of the examples showing the operation at significantly, distorted current. We have nonlinear current, we have asymmetry, we have both together, but all the time, even with very small capacitor, using this control trick, we can provide all the time pure sinusoidal voltage to the final end user. And some of the overall problems which is related to the distributed control platform. So especially that our demand was that we are using the silicon carbide components, so with switching frequency 100 kilohertz. Also, we should have the hard real-time control. We should provide a synchronization. We should provide some of the flexibility to have the hot plug and reconfiguration. We also should provide reliability, parallel operation of the modules and leg power management. Therefore, we see that final control, it's really complicated, including the many of the layers. The first layer, which is indicated here, of course, includes some of the internal control loops, including the modulation, including the voltage control, current control, what is, I think, very important for the single converter operating. But when we have a modular converter, then we have to take in account also the second stage of the control, including also from medium voltage side, like active and reactive power, with harmonic compensation, voltage unbalance, voltage support. From the isolation DC-DC converter, there's integration. We can include, for example, integration of the electric vehicles. We can control power flow. We can provide power flow limit. On the low voltage side, we can provide like a load identification, because we can save the energy in the batteries, in the energy storage, when we have, for example, the long identification, or we have can provide harmonic resonance control. We have the dynamic voltage control. So we can see that there are plenty of functions which have to be somehow included together. And we have a top layer, and the top layer includes the system control. When we have the stability issues, we have the data collection. We have different operation mode. What I told, that we have the mode to operate with the constant power, the symmetrical current on, we can support some of the phases where the short circuit appears. And we have a territorial control when we have demand side management, and we have interaction with another solid state transformer. And from the communication point of view, if we are thinking about the post-fault operation, if we are thinking about the converters be able to make a reconfiguration to all the time provide the service, also we should consider on the same level some of the redundancy in case of the communication. Therefore, we have to use such two options, which is a ring one. Then we have even if there is a break-in connection somewhere, then we have the two directions to deliver the message to the node. Or we can use this parallel redundancy with the two switches. So even if one switch is broken, then we can deliver the message to the final node when the message finally should be delivered. And for these purposes, to provide the communication among the modules, we propose we use EtherCAT, which from our point of view was the most convenient solution, which gives plenty of the advantages, including the high speed, which was possible for some of the control layers. It gives topology flexibility. It's also provided scalability, redundancy, and synchronization. So from our point of view, therefore, we use this protocol for communication. And when we look for the final topology, we see the plenty of the converters together. So to control all of them, At the same time, you see how difficult it's to use the control, because we can count here plenty of the local controllers, including the DSP, as well as we need some of the master controllers, one master controllers for the top control layer, and we have the master controller from medium voltage AC to low voltage DC, and we have a separate also low voltage DC to AC controller. So we see that of course, the control issues are quite difficult, but to provide a reliable communication between the modules are also demand and a challenge to final implementation. And some of the conclusions. Of course, I will repeat some of the conclusions that smart transformer deliver plenty of the advantages, and we have to remember about this that for example, if you are looking for hybrid system, including the DC link and AC voltage, there is a perfect proposal. If we need proper operation, the voltage unbalance or different distortion like a voltage dips and other disturbances, also the smart transformer it's a good option for consideration. If we are thinking about increasing the efficiency of the smart grids, because we can control dynamically the power flow, or when we are thinking about the transactive energy concept, then it's also like a hub. It's the smart transformer. It's an interesting option. Also, we have more advantages like reactive power and high harmonic compensation. We have the dynamic voltage control. We have the communication. We can provide the communication with other elements to smart grids, because if we have the smart grids in the another nodes, but then finally we have the traditional transformer, then we lose something in our smart grid. And we can provide the full control of each individual phase and simple unwinding mode of operation. But there are also some of the challenges. This is why we still have the solid state transformer ready for market. So design and construction, it's still more expensive in comparison to the conventional transformer. We hope that, of course, that new technology brings some of the new semiconductors, which making this disadvantage. Which eliminate disadvantage, and we will be able to tell that on the cost point of view, it's smart transformer. It's also competitive. We still have a problem with reliability. This reliability can be solved by the post-fault operation and some of the possible reconfiguration of the system, but it's not easy issue, and of course demand still new solutions. But the new papers showing also the power routing make a hope that this problem can be skipped in the future. Also, another challenge which have to be solved, it's low short circuit capability in comparison to traditional transformer, which make the use of regular fuses rather complicated. Also, there is system, it's very fragile for communication errors. If we come back in our mind to some of the previous slides showing how complicated communication system is demanded, then we can feel how difficult and how fragile is this communication. And also, if we are thinking about the so smart hub, we have to still remember about the possibility of cyber attacks, and we still have to be considered as a challenge to be skipped. So if we ask what's the next step for the smart transformer applications, from my thought and from my perspective, it's a hybrid transformer. So from my perspective, we are not ready to implement already or replace the traditional transformer by the smart transformer, but we are ready to make some of the hybrid transformer, which provide many of those functionalities presented by me, and at the same time we have the high reliability and high short circuit power provided by the classical transformer, and we can use them in different scenarios, different options, like hybrid transformer with virtual inertia, with or hybrid transformer with electric vehicles charging station. But the deep analysis of this you can find in this paper, which was published this year, maybe 1 month ago in Energies. And of course, the last option is to use together with the PV, which is very natural. So thank you very much for your attention. Exactly, I use my time for this presentation. So thank you very much again for the attention. And I would like to acknowledge to my colleagues who work together with me in during the project, which was called Team Tech. Thank you.
Thank you, Mariusz, very much for your excellent presentation and on time, keeping time. So we have now a time for questions, comments. So the floor is open to the audience. We are waiting for your question. You can also write them on the chat.
We have something on the chat.
You can check the hand which are raised.
Maybe if I can have a couple of questions.
Yes, please, of course.
Mario, thank you for a very nice presentation. I have fundamentally 3 questions. The first, did you consider the source switching configuration of the converters around the transformer, which was in the past also used?
No, we from the beginning we not considered this option.
Yeah. So my second question is, how do you solve the problems with the grid overvoltages, which are very frequent and very dangerous for the operation of the grid connected part of the solid state transformer?
So, sorry, could you repeat? I'm sorry, because I didn't hear the first part of the question.
Okay, the problem with the grid overvoltages.
Okay.
Which stress the part of solid state transformer which are directly connected to the grid. I mean the input and output converter.
Yeah, of course, we consider only like a 30% over voltage, which can appear in the grid, because when we can see some of the operation of statistics, then we can see that we not observe the higher rise of the voltage in such situation.
Mm-hmm. And my third and last question is, did you make any analysis in which power range the solid state transformer can be competitive solution?
In this situation, as I told that in current situation, I think that the solid state transformer in current version, which it was presented, is still not ready for the application. So from my perspective, my thought is only that if we are consider some of the hybrid solution, it's only competitive solution for the industry.
Yeah, because I think it is very similar situation like with the solid state transformer in the traction application, which were researched deeply 10, 15 years ago in 2005, 2006, when many leading companies invested their money into the research of medium frequency transformer configuration for multi-system locomotives. Mm-hmm. And the technology is mature enough. Nevertheless, the problem is with the reliability and with the cost. And there are the pilot operation of this technology. Nevertheless, they are not up to now the serial produced devices with this technology. And I'm afraid that we are in the same situation with the solid state transformer in the power grid.
Yes, as well as I think it's also remind me another situation when, for example, the ABB applied for the diode rectifier for the traction with some of the active, partly power active rectifier. It also, they not decided to replace fully diode rectifier by the full active rectifier, but they only partly replace to provide some of the additional functionality, as I told. So it's absolutely from this, I think that the same source of the problem.
Yeah, therefore I think that definitely the solid state transformer will play an important role in the low voltage grids and in the lower power ranges, where this technology can be beneficial in comparison to the transmission lines, where we are talking about the extremely high voltage and extremely high power. This technology will still not be competitive to conventional technologies in next 10, maybe 15 years, I think.
True, absolutely true. Therefore, as I told that maybe if we are considering the hybrid solution, maybe we are able to convince the industry. Maybe we are able to convince the power system operators. Otherwise, nobody decide to use the smart transformer replacing the classical transformer because of those doubts which you express also. Therefore, I fully agree that we need like a 10 or 15 years if we are thinking to completely replace the transformers in some of the applications. But we have to remember that the reliability, it's a key issue for the industry.
Yeah, thank you, Mariusz.
Thank you.
Okay, is there any more question from the audience? I think as we are already a little bit over time, we could now close the session. Is there any announcement from the organizers for our?
Just to invite everybody for parallel sessions at 2 p.m. Central Time. So in 10 minutes, you can join if you're interested. And don't forget to join us for welcome reception at the evening to exchange some informal ideas.
Okay.
Hi, Mariusz. May I ask one thing?
Yes, please.
Yeah, I wonder the control system behind you. Is it in your laboratory or anywhere else?
The system is everywhere. You know.
No. I think this is what in the background.
Okay,
of my background.
I have the same system in my laboratory in Ankara Gazi University. So it's similar.
No, I think that you have the more modern, because this is what you see in my background. I rebuilt as for some of the historical exhibition, showing the first power plant in Poland, and I built using the real devices from the beginning of the 19th century.
I mean,
of the 20th century. Sorry, 20th century.
Made by the German technology long time ago, still in use.
So good, but this is what I built. Okay. But historical exhibition.
So we should keep it.
So sorry, Mariusz, I like your background, but I would like to suggest for all presenters to use the PMC background, which you can download from the website.
We
do in the future.
Yes.
Okay.
Mariusz, hope it still operates the system behind you. So this is, is this working or not?
No, I built it like 3 years ago, and it was not operating ever, never. It's just only, as I told, it's a part of the exhibition.
So let's continue next sessions.